The second question that was requested was a question on finding equivalent systems, specifically finding one that involves a lever arm instead of a couple moment. And I'll do both of those with this problem here. So in this case, I want to replace this loading with an equivalent force or a resultant force and a couple moment that's acting at point O. So in this particular case, I've got two triangular loads here that are shown, and I've got a point load here and a couple moment there. So I need to account for all of this as I'm building my equivalent system. Remember, my goal is to replace all of this with a simple system. So I'm just going to replace all of this with a simple system of some resultant force. In this case, I know all of my forces are going to be acting down, so I can kind of make a prediction about what I think this is going to look like. I think I'm going to have a resultant force that acts straight down. Sometimes it'll detect this correctly. There's my resultant force acting straight down. And then I'm going to have some couple moment that's going to be acting at O, something like that. Let's call it MO actually instead of MC. I think it's more important that we know its location than know that it's a couple. We kind of imply it's kind of implied, right? So that's my goal, is to find that. That's my find. We will then, after that, our second half, we'll take this and we'll go, hey, how do we replace this FR with or this couple moment with a lever arm distance? Placing FR at a particular location measured from O. I'll put those support reactions back in. Cool, since we're only looking at the loading here. Okay, so this is what we have. Our first goal is probably to break this up a little bit. I'm gonna break this up a little bit. I want to break this into triangle 1 and triangle 2. And thinking about those, I'm going to go ahead and draw those what I think the equivalent force where those centroids would be for each of those. Approximately, we'll call this force 1 and force 2. So to get our resultant force, let's start with that. That's our step 1. Find FR. FR is going to be the sum of F1 plus F2 plus the 15 kilonewtons. F1 is just going to be the area, so that'd be like 1/2 7.5 times the magnitude, which is 6 kilonewtons per meter, plus 1/2 4.5. Now the reality of this is one big triangle, so for finding area, we could actually just do 1/2 of the total length. I'm going to do that instead. We'll probably want to break this up later, so I could calculate these separately. It's up to you how you want to do this, but let's do it separately since I know I'm going to use it next. I'm going to change my mind a little bit. Plus the 6 kilonewtons, 1/2 times its length, 4.5 times 6 kilonewtons again, plus 15. And I'll leave you to do the calculations. And remember, at this point, I'm trying to solve problems and practice that skill, go fast. Practice more problems, look at the engineering part, don't worry about the algebra, but I'll get a sum of forces from this. That's my goal, right? That's what I'm going to get from this step. Step 2 is we need to find the lever arms. And I'm going to do a little bit of the detail work here because I want to make sure I practice the lever arm skill. That's going to be important. We want to find MO. MO is going to be equal to, well, first we got to make sure we include this 500 kilonewton meters, and that's going to be a clockwise right-hand rule. That's going to be negative kilonewton meters. Lever arm for F1 is going to be 2/3, right? Because we're from the skinny end here, 2/3 times 7.5. And F2, we'll talk about the sign in just a second, is going to be the 7.5, this distance here, the 7.5 plus 1/3 plus 4.5 divided by 3. Both of these are going to be negative as well because they're going in the same direction. You can use that right-hand rule to prove that to yourself. So I'm going to get a pretty negative number here. And then I've also got that 15. So I don't want to forget about that lever arm. 15 times its lever arm, which is the full 12 in this case. 12 meters. My answer in this case is going to be the resultant moment in terms of we're talking about kilonewton meters here. All right. So then we would have those two answers. We could pop those in here and we're done with the first step. That's the easy part right there, right? To find FR, call this the next step over here. To find FR, to find distance D, remember that distance D that we're trying to maintain is to keep these two systems the same, which means that our moment is force times that perpendicular distance, or MO divided by F R is the same thing. So I've already found M naught. I got that, or the MO here. Got that value. I've got FR, and that's going to give me my value here. And I know it's measured which way? I know this is going to be measured from the right. We got to be careful here because I know when I do this calculation, I'm going to get a negative MO, and I'm going to get an FR in here. And you might be tempted to go, oh, that's D, that's negative. D's got to be measured this way, right, to the left. And we know that that's not the case, right? Why do we know that's not the case? We can look over at this problem right over here. On the left side, the equivalent system says, hey, MO is clockwise, right? We need to maintain that same clockwise direction. So just keep that in mind as you solve this problem, that you're keeping that straight, making sure that you're getting your D measured correctly from O to the right, which makes sense, right? That's where our centroid would be, is if we're just looking at this as a equivalent force system, or these is just weights, right? It wouldn't make a whole lot of sense for our weight to be off the beam on the left because we don't have any load over there. That's our other sanity check.